we continue our study of rules of inference. As we stressed in the previous video, the rules of inference we know can be used to derive new ones, so it's useful to refresh which rules of inference we already know. Well, every logical equivalence that we know generates two rules of inference, one for each direction. For example, we know about double negation. A statement is equivalent to its double negation. There are various commutative properties. For example, P and Q is equivalent to Q and P. There are a couple of associative properties. There are also various distributive properties, including De Morgan's laws. These govern logical equivalences behind mixing together ands with ors or conditional statements and negations and so forth. We also discussed two other rules of inference, modus ponens and modus tollens. These relate to how we can use conditional statements with other bits of information to extract new information. Now, one of the known logical equivalences involving conditional statements that we have is the following. P implies Q implies not Q implies not P. That can be shown to be a tautology through a truth table. We refer to this as contraposition. It's a rule of inference. It has a single given, a conditional statement, and it allows you to derive another conditional statement where instead of hypothesis implies conclusion, it's negated conclusion implies negated hypothesis. Okay, there are a bunch of other rules of inference that we can establish through truth tables, and we're going to go over them. So the statement P and Q implies P. That's a tautology. If P and Q is true, well, certainly P was true. And you can show that with a truth table. We're not going to bother doing that. The associated rule of inference is called specialization, and here it is. If you have a statement P and Q, well, then you can extract the thing on the left, P. We now propose a following rule of inference, which we can prove. We could draw up a new truth table, and it's very similar to the one we already know. P and Q implies P. This is just P and Q implies Q. But let's actually do it as a two-column proof. Here it is, okay? So what we are trying to prove is this rule of inference. It has a single given, P and Q. I apply the law of commutativity and say P and Q is logically equivalent to Q and P. So since I have one of them, I can automatically derive the other. Now we're going to use this rule of specialization. If you have a conjunction of two statements, you can extract the one on the left. We have a conjunction of two statements, so we extract the one on the left. From the given P and Q, we were able to get to the conclusion Q using existing rules of inference, so we've derived a new rule of inference. We're also going to call it specialization. Point being, if you have a conjunction, you can extract either the left side or the right side, both of which we will call specialization. We can abbreviate this as canceling out or subtracting the conjunction or and sign. Next, we have disjunction. The following is a tautology. P implies P or Q. You can understand this intuitively. If P is true, well then certainly P or Q is true. It gives us the following rule of inference. We propose a new one, okay, that rather than from P, a disjunction with P on the left, you can also do from P, a disjunction with P on the right. And the two-column proof is going to be very similar to the one from the previous slide. It has a single given, P. If I use this rule of inference, from P I can extract P or Q, but by the law of commutativity, P or Q is equivalent to Q or P. So from P, I was able to get to Q or P, so this rule of inference has been shown. This, unlike the last one, instead of canceling something out, from a known statement, we are adding in a disjunction, so we can abbreviate this as plus or you can just call it disjunction, either way. Now let's take a look at conjunction. This is a little tricky to write out as a logical equivalence, but if you have P and Q, that is equivalent to having P and Q. Written as a rule of inference, it's actually a little clearer. If you have P and Q, you can deduce the combined statement P and Q. Notice that it has two hypotheses, so if you want to use the rule of conjunction, you have to refer to two lines, and then the line you get out is exactly those two lines with a conjunction sign in between them. So we propose that instead of from P and Q getting out P and Q, you could also get out Q and P. Just like before, okay, notice we have two givens, so we state them. If I apply the rule that we already have, I can extract P and Q, but by the rule of commutativity, P and Q is the same as Q and P. So from these two givens, we were able to work our way towards this statement. So this rule of inference has been shown. Either one of them is going to be called conjunction. You can abbreviate that as adding in the conjunction symbol, and it's pretty straightforward to use. If you ever can refer to two statements, you can just make one new statement that's both of them put together. Next up is resolution. This is a very important rule of inference that comes from the following tautology. Okay, you can prove this with a truth table. As a rule of inference, it looks like this: P or Q and not Q, therefore P. You can abbreviate this rule of inference as canceling out or removing an or sign, because from one of your givens that has an or, you end up with something that doesn't. Without bothering to construct the proof, you can do something very similar. Rather than having a disjunction and a negation of the right argument, from which you extract the left one must be true, if you have a disjunction and a negation of the left argument, you conclude that the right one must be true. Either way you refer to this as resolution, there are two givens, so you better refer to two lines. One of them has to be a disjunction, and the other has to be a negation of one of its arguments. What you conclude is therefore the other argument must be true. Intuitively, this simply says, if you know either P or Q, but it's not Q, therefore it must have been P. Alternately, if you know either P or Q, but it's not P, it must have been Q. And that's the rule of resolution, a very important one that we will make great use of. Moving on in our study of rules of inference, here's one called conditionalization. Okay. Both of the following statements are tautologies. You can prove so with a truth table. Q implies P implies Q, but also not P implies Q. They're both referred to as conditionalization. As rules of inference, they look as follows. From Q, deduce P implies Q, or from not P, deduce P implies Q. Either way, this can be abbreviated as adding in a conditional sign, and it's a really tricky one to use. Okay, so notice, in the first form, you have the statement Q, but P can be absolutely anything. So from this statement Q, you can introduce a conditional statement whose hypothesis is anything at all you want. The letter P, or through the use of substitution, any other statement here. Similarly, if you have not P, you can introduce the conditional statement P implies Q, where Q is any statement you want. They don't have to have anything to do with the one line you referenced. So for example, suppose you have the line Q or S. Just pretend that was justified. Since I do have this, I have a line, I can automatically make it the conclusion of a conditional statement using any hypothesis I want. For example, P or R implies not S. So from the known line Q or S, I can make this conditional statement. But I could have put anything I wanted here as the hypothesis. It really wouldn't matter. They'd all be justified. That amount of freedom is kind of scary because it's not really clear often what hypothesis is going to be helpful because they are all allowed. So it takes practice to use this not just correctly, but also in a useful manner to completing your proof. Let's make a remark on double negation. Usually, anytime you use a rule of inference or a logical equivalence, you have to be extremely specific about it. But we're going to allow double negation to be buried as a line that you don't necessarily do by itself. So for example, suppose you already had the line not P implies R, and you have not R, and you want to apply modus tollens. You have a conditional statement and a negation of the conclusion. Well, if you apply modus tollens to a conditional statement and the negation of its conclusion, what do you get out? The negation of its hypothesis. Very strictly speaking, that would be negation P. But we know that not P is equivalent to P. So rather than give a new line of not P and then go to P, we just say, look, double negation is a very simple step, and we're not going to bother doing it as its own line when it pops out of things like modus tollens. So this is okay. Similarly, if I know not S or not Q, but I know Q. Now, if I want to apply the rule of resolution, what I need is an OR statement, there it is, and the negation of one of its arguments. So very, very strictly speaking, if I had Q, I would have to do not Q, and then I can do resolution. But again, that's a very straightforward use of double negation that we don't really require to be its own line. So we are usually fine with saying, you know what, just go straight to the resolution in line 8, and we all pretty much see what was going on there. So double negation is typically allowed as a hidden line. Don't ever hide things like modus ponens or distributive properties, though. Double negation and substitution are really the only things that we allow to happen in the background without being extremely explicit about. Let's work through an example of a two-column proof. Okay, this is a valid rule of inference, but let's prove it. So here's your hint. This is as long as it needs to be. I've given you 6 of the 8 lines as statements, and then I've given you justifications for the other 2. So pause for a minute and see how you would bother to fill this in. Otherwise, I'm just going to work through it right now. Okay, hopefully we took a minute and tried to figure it out. Well, the first 3 lines are exactly our givens. So those are the justifications for lines 1, 2, and 3. Now, how can I get line 4? Well, it's got to refer to one of the lines above. Looking up here, I want to get out something involving Q or R, and that looks like it might have something to do with here. But the only way to extract this would be to resolve this disjunction, which would require me to have a not P, and I don't have a not P, so that can't be it. But what about this line right here? This is a negation of a conjunction, and by De Morgan's law, the negation of this conjunction, Q and not R, will be the same as not Q or not R, and with one of those hidden uses of double negation, I can ignore that not. And that's exactly what we have here. So this is De Morgan's law, one of our distributive properties, applied to line 2. Okay, even if you didn't get that justification, you could have asked, what about resolution between lines 3 and 4? If I have line 3 and I have line 4, resolution involves finding a disjunction, here it is, and a negation of one of its sides, there it is. And what do you get out of it? The other side, which is not Q. So by resolving the disjunction, either we didn't have Q or we have R. We don't have R, so we must have had not Q. And what about line 6? If I want to use the law of associativity on line 1, there's really only one way I can do it, and it's this, P or R or Q. Associativity allows me to move those parentheses around as long as we're not mixing together conjunctions and disjunctions, and we're not, these are both disjunctions. So I move the parentheses over there, that's the associative property of disjunction. Now let's look at line 7. Well, look at lines 5 and 6. Either the thing we want to get, or Q, but we don't have Q. So by applying resolution to lines 5 and 6, we can get out that left argument of P or R. And now how am I going to get line 8? The desired conclusion, P. Well, we haven't used line 7 yet, P or R. How can I get a P out of this? I can do resolution again by going back to line 3. We haven't used line 3 except here we did. Okay, so try to look for lines you haven't used or that you've only used once, maybe, to see what should be useful next. So again, if I apply resolution to lines 7 and 3, we're going to get the desired conclusion P. And now let's see what we've got. Having stated these 3 givens, then used legitimate rules of inference, we were able to extract the conclusion P. So anytime these three things are true, it must follow that P is true. So there's that rule of inference, and here is a nice two-column proof. Now there are other ways you could state these three givens and arrive at this conclusion. You should never feel that because two people come up with a different two-column proof that one of them must be wrong. It's possible, of course, but it's totally possible for two people to come up with different but still correct two-column proofs. Okay, let's work through another example. From these givens, can we get to this conclusion? Okay, well, let's just work through this manually. No hints. Well, lines 1, 2, and 3 are very straightforward. They're just going to be our givens. You can always start a two-column proof by writing out whatever the givens are. Okay, and depending on your instructor's generosity, that might be worth very little credit because literally every two-column proof begins with it, or it might be worth a good amount because, hey, you at least started correctly. We also know, by the way, how this is going to conclude. I don't necessarily know how many lines it's going to take, but I know the last thing I'm going to write is this. Okay, it might not take this long, it might actually take more lines than this, but I do at least know that at a certain line, with a certain justification, I'm going to get there. And this is worth pointing out. Even if all you can do is state the givens and state the desired conclusions, you've at least said, not only do I know how the proof has to start, I know how it should finish. Okay, this is communicating useful knowledge to your instructor that you know some stuff. But now we have to start playing around. What can I possibly say with the givens that I have? Well, is there any way to combine lines 2 and 3? There is, because I do have two different things, I could conjoin them. I could say not G and not L implies not W. And that could be conjunction between lines 2 and 3. That would be legitimate, but it doesn't look very helpful. I don't see how that's going to get us anywhere closer to our desired goal. So I don't think that's what we want to do. Again, it's allowed. I just don't think it's very helpful. Okay. Since I don't have G, however, you know what I don't have? I either have not G or not L. So this is a little tricky as a first step to come up with, because it's not immediately obvious that this is helpful, but it's definitely allowed. This is just disjunction, aka the addition of the or sign applied to line 3. I took something I had, not G, and I said, well, either that or something else. Why is that helpful? I'll give you a hint. Apply De Morgan's law to it. If I apply De Morgan's law to line 4, what do we get? Not G and L. And now we're kind of getting somewhere. What can I do with the negation of G and L? I can combine lines 5 and 1. How can I combine lines 5 and 1? Well, I have negation of G and L, and here I have G and L or something else. So we're going to use resolution. And what do we get out of it? W and S. Now, anytime you extract a conjunction, not the negation of a conjunction. When you have a conjunction, I kind of recommend immediately doing two things. Get both of its individual components. Okay, this is specialization, or the elimination of the and applied to line 6. It's not necessarily true that both of these are handy, but maybe it is. Now, what can I do with either of these two things? Well, let's look at our givens. Okay, we're not usually in the habit of giving trick problems. The givens are going to be used. Have we used line 1? Yes. Have we used line 3? Yes. We have not used line 2. So if you have a given and you haven't used it yet, keep that in the back of your mind because maybe you want to. Well, line 2 is a conditional statement. While there's other stuff we can do, most common would be to use either modus ponens or modus tollens. If I want to use modus ponens, I need to have the hypothesis. That would be L. I don't have L. If I want to use modus tollens, I need to have the negation of the conclusion. Well, the conclusion is already not W, so by a hidden use of double negation, the negation of that would just be W, which I do have. So we can use modus tollens between lines 2 and 8. Not 8, sorry, 7. If I use modus tollens between this conditional statement and the negation of its conclusion, what do we get out? The negation of its hypothesis. So we're going to get out L. And now we've used all of our givens. It doesn't mean we won't use them again, but once you've used them once, it's probable you're not going to use them for something huge. Okay, I mean, you certainly could. Okay, we had line 4, 5, 6, 7, 8, 9. Where are we trying to get S and L? How would you ever get a conjunction? Well, there are a couple of ways, but one of the most straightforward would be through the use of conjunction, the addition of the and sign. In order to get that, you would have to have each of its sides individually, which we have as lines 8 and 9. So I can get right here as line number 10. So from the top, we stated our givens. Here's the tricky step. If I have not G, then I can say I either have not G or something else, and of all of the somethings, I put not L here. This was just a little bit of foresight to know that I'm going to want to negate this through use of De Morgan's law so that I can resolve this disjunction and get out W and S. I didn't necessarily know that W and S was going to be super helpful, but since we are trying to get S and L, getting out S is at least halfway there. Now the other thing we get out is W, which could combine with the given we hadn't used yet through modus tollens to give us our missing L. Now we have S and L together, so by conjunction we're done. Okay, so this is a nice example of a two-column proof. We will do many more examples to get further practice.